Okay, welcome guys. So in a previous video, So we prove, okay, now we prove, I proved that some application of the homomorphism theorem. Okay, so in this video, let's go to the final results. Basically, it's the second and third homomorphism theorem. But basically, they are saying the correspondence theory in the group theory. Okay, so let me just start. I hope you guys subscribe to my channel. Okay, so remember that our general settings that we have a group G and a group homomorphism phi from G to G bar. Okay, and let's say we have the kernel is K. So the kernel phi I call it K. Okay, let's denote it. Let's denote there is a H bar as a subgroup. Okay, and H, let's define H to be the image. Okay, so that H to be the inverse. So X belongs to G such as phi of X belongs to H bar. Okay, so this is just the inverse, right? Phi inverse H. Okay. Okay. Okay, so now so this is our setting. So we need to somehow give the correspondence theorem says that we want to classify the H bar, or basically found the relationship of H bar and H, right? So H is just image. H is a pre-image of H bar. Okay, so let's see what can we say. Okay, so let's say okay, so let's say the results. Oh, so the first result is that H is a subgroup. If suppose our H bar is a subgroup. So basically, if H bar is a subgroup, then the pre-image is a subgroup. Okay, and the second is that H will cover the kernel. Okay, this is trivial because in H bar there's an identity, and the kernel just map to identity. So H must contain kernel. Okay, so now let's see how to prove. So 2 is trivial, so that's proof 1. Okay, so let's say if X Y belongs to H, then we have phi of X belongs to H bar, and the phi of Y belongs to H bar. Okay, so we know that phi of XY equals to phi of X, phi of Y. So this belongs to H bar, this belongs to H bar, so they both belong to H bar. Okay, so therefore XY belongs to H. Okay, so this shows that the closure. Okay, so now let's see if X belongs to H and phi of X belongs to H bar, right? Because definition, which tell you that the phi of X inverse is just phi of X inverse. So phi of X belongs to H bar. So phi of this belongs to H bar. So it tell you that X inverse belongs to H. Okay, so this tell you that H is a sub. Okay, so this is just a pre-image. Okay. Okay, so how about we add how about H bar is a normal? Okay, so let's make an assumption that if H bar is normal, then see what we get. Okay, so if H bar is normal, then that's this. Okay, so what happened? Yeah, if H bar is normal, let's say we have group G. We take element G, it belongs to G, and H belongs to H. And then what we have is phi of H belongs to H bar. And then we also have phi of G, H G inverse is just phi of G, phi of H, phi of G inverse, right? And you see this belongs to H bar, right? Because we assume that H bar is normal. So which tell you that G inverse belongs to H bar. Okay, so which tell you that H is normal in G. So which tell you that if H bar is normal, then you will imply that the H is normal. Okay. Okay. And by definition, right? By definition, sorry, not by definition. Okay, so now let's see. Let's see what I'm going to say. Yeah, so in the previous settings that our H is just taking some subgroup, Okay, so but now that's by the okay. So let's restrict. So now we have this, and we take this, right? Which is pre-image. So its pre-image is H. Okay, so we can use in the case here, right? So we can use the first isomorphism theorem. So that means if we focus on this subgroup, we get H quotient K, right? H quotient the kernel, because the kernel of the G is the same as kernel H, right? Because H is a subgroup of G, so H modulo K will isomorph to H bar. Okay, so this is also the results. Okay. Okay, so this is the one directions. This direction tell you that if you take H bar, you can construct H. So it's fine. You can construct H, and which H quotient K will be H bar. Okay. And then let's say conversely. So let's see if we have H, then how can we construct H bar? So this is another direction of the correspondence. Okay, so let's say we take the subgroup of G, which is called L, and we get the K is a subgroup of L, and we can denote L, this L bar, right? Just be image of phi. Okay, so exercise for you to show L bar is a subgroup of G bar. Okay. Yeah. So, let's see. Okay, so let's say so now we got L bar, right? L bar is image phi, so it looks like X belongs to G bar such that X bar is phi of L, right? L belongs to L. Yeah, so easy exercise will show that L bar belongs to G bar. Okay, so I want to show that this L bar is unique. It's unique. Okay, in a sense that suppose you take a group T called Y belongs to G, phi Y belongs to L bar. Okay, so that means I pick this L bar, right? And take that phi Y belongs to L bar, and I take that Y belongs to G. And we can I want to claim that T is just L. Okay. Okay, so clearly by definition, L belongs to T. Okay, this is the usual set theory exercise. Now you can check that because L bar is defined to image, right? But I asked the inverse. So I asked what is the inverse of this, right? So L will be subset of T. So we need to ask that is there T, the element T belongs to T, which T do not belong to L. Okay, so let's see if such T exists. Okay, so if such T exists, we know that this phi of T must be also L bar, right? So by definition of L bar, this phi of T will be phi of L for some small L belongs to L. Okay, which tell you that the phi of TL inverse will be phi of T, phi of L inverse, which will be identity in the G bar. Okay, so TL inverse belongs to K in L. So which tell you that the TL, this small L, right? Because TL inverse belongs to K in L. So by definition, you get L. L will be L. Right, so this T will be right because LL in L, right? And the TL inverse is set in L, so T will be in L. Okay, so such that T is the same, T is subset of L, so T must be L. Okay, so now we develop the correspondence. So combine all we say, then we have the following theory. So theorem. If phi is a group G to G bar with the kernel K, so kernel phi is K, then you take the H bar as a subgroup of G bar. then you can define H. So you can define H to be the preimage. So X belongs to G such that phi of X belongs to H bar. Okay. Then H is a subgroup of G. And also H contains K. So this is one direction. If somebody gives you H bar here, then you can construct this one. Okay. So conversely, and also shortly is just if H bar is normal in G, then G bar, then you have H is normal in G. Okay, and then this is a one-to-one correspondence. So it means any H bar will only give you one H, and any H from left from between K and G will corresponding to another H bar, which is just a direct map. So this is the correspondence theorem. Okay, yeah. So we finish this. Okay. Or basically, I can just add I can add using a sentence. One-to-one correspondence from the set of all subgroups of G bar onto the set of all subgroups of G containing K. So any subgroups from G containing K will one-to-one corresponding to the subgroups of G bar by relating this phi. Okay, so this is the correspondence theorem. Okay, so let's finish this video by the final theorem. So you get G to G bar, kernel K, kernel phi is K. And what we want to show that, let's say you have a normal subgroup of G, that's called N bar of G bar. And you can construct a preimage. So let's say N is just a preimage. Okay, so and we already proved that it's N containing K. Okay, and the theorem tell you that G quotient N will isomorphic to G quotient N bar. And also G quotient N will the same as isomorphic to G quotient K, N quotient K. Okay, so this is the third isomorphism theorem, usually written as this way. Okay, so which tell you that, okay, so first says that the G quotient N, right? So there is N here. Okay, so G quotient N will be the same as G bar quotient N bar. So this is the first theorem. And the second theorem tell you that G quotient N, so G quotient N will the same as G quotient K, right? Because K is a smaller one, G quotient K over N over K. Yeah, so it's the same as just delete this K. Okay. Okay, so proof. Okay, so we already know that there's homomorphism of G bar onto G. So this is the quotient map, right? G bar map are surjective to G bar quotient N. And then you will say that G bar will define to be G bar N. Okay. So we need to let's construct, and then we also construct a map. We can construct a map phi to G bar, G quotient N bar, such that by phi of G. So this is what I define to be N bar phi of G. Okay, so this is the okay. So let's focus on this map. Okay, so first phi is onto, and the reason is that let's say you take any G bar belongs to G bar. So you need to prove it's onto, right? So a little bit tricky. So let's see. You need to prove it's onto, right? So that means you take any subgroup of this, you hope to find G. So let's say you take G bar belongs to G, and then we hope to show that G bar equals to phi G for some G belongs to G. Okay, but we know that phi is onto, right? By definition, right? Phi is onto. Why phi is onto, right? Because N bar will map to something called N, right? So by the way, we need to make an assumption that this is onto. So G map to G bar must be onto. Okay, sorry about this. We need to add so this map must be onto. Sorry, I forgot this assumption. So this map must be onto. Okay, so now we can use phi is onto. This is assumption. If phi is onto, right? So the typical, so this n bar g bar in g quotient n is basically represented as n phi g, right? Because phi is onto, this phi is onto, right? So I can always find something mapped to. So this is basically trivial. Since my assumption of phi is onto, right? So it will directly imply psi is onto, because phi of g, you can always find something mapped to phi of g. Yeah, so it's real such. Okay, so let's see. Let's see if AB belongs to G, and we have psi AB equals to n bar phi AB. So this is a definition. And we know that phi is homomorphism, so this is just n bar phi AB, phi B, which is n bar phi A, n bar phi B, right? Because n is normal, so you get psi A and psi B. So which will tell you that psi is also homomorphism. Okay. So phi G from G bar quotient n bar. Okay. And it's also onto. Okay, so we ask what is the kernel. So what is the kernel? Let's see. Okay, so if you say n belongs to n, then your phi n will be n bar, right? So psi n will be n bar phi n. But phi n is n bar, so this is n bar, right? So you know that n is basically the subset of the kernel. Okay. Okay, so on the other hand, we need to show that I want to show that kernel psi is just n. Okay, so let's say if you pick up t belongs to t, and your psi t is identity, basically just n bar, right? But definition is just n bar phi t. Definition. So we'll tell you that phi t belongs to n bar. So t belongs to the pre-image, right? Phi inverse n bar. So by definition, phi inverse n bar is n, right? Definition. Okay. So that means that the kernel of psi is just n. Okay. So now we have construct a map from G to G bar quotient n bar, which the kernel psi is just n. Okay, so by the first isomorphism theorem, G quotient n will isomorphic to G bar quotient n bar. Okay. Let's say the second, right? So the second is I already proved in a previous in the first theorem that where, right? So if you have this, then you get this, right? So now your G bar G quotient K. If it's onto, right? So this is the second, you use the isomorphism again. So G bar is G quotient K, and also you restrict it in n. So you restrict the map to n bar, right? So it's still onto. So by the first isomorphism theorem, again, n is just G quotient n. Okay, so you write in you restrict it into n bar, right? So now this original map change it to n bar, right? So you get n quotient k. So n bar is just n quotient k, and then G bar G quotient k. So you put in. Finally, you get a G quotient n isomorphic to G quotient k and quotient k. Okay, so this is the third isomorphism theorem. Okay, nice. Okay, see you guys in next videos.